Here's example 8 of evaluating trig with inverse trig. So we're going to use this flowchart again that we've been using. And if you want a copy of this flowchart, check the video description. There's a link in there. You can click that link, open this up, print it out, and follow along if you'd like. So example 8, cosine of the inverse sine of 11 over 12. So we'll start here at the top. Is there a domain violation? No, there's not, because we can take the inverse sine of 11 over 12 because 11 over 12 is between negative 1 and 1. So remember, when you take the inverse sine of something, it has to be between negative 1 and 1. Okay? And 11 over 12 is between negative 1 and 1, so it's okay to take the inverse sine of that. And then we can take the cosine of anything we want. The domain for the cosine function is all real numbers, so that's fine. So no domain restriction there, no domain violation. Is the function paired with its own inverse? Well, no, because it's cosine paired with the inverse sine. So cosine and inverse sine. It's not cosine inverse cosine, not sine inverse sine. It's cosine inverse sine. So is the function paired with its own inverse? No. Can the problem be solved using the unit circle? No, because another way to ask that question is this a nice number from the unit circle? No, 11 over 12 is not a nice number that appears anywhere on the unit circle. Okay, so it's nothing like it's not pi over 6, it's not 0, it's not 1, it's nothing like that. This is not a nice number, so no, well, it's not a nice number from the unit circle. So no. Can this problem be solved using the unit circle? No. Is the inverse function on the inside? Yes, it is. Okay, inverse sine, that's on the inside, and the regular cosine is on the outside. So the function is on the outside, the inverse function is on the inside. So is the inverse function on the inside? Yes, so we use reference triangles. Okay, so that's how we're going to do this problem, is with reference triangles. So how do we do that? Well, let's just go ahead and get started. Okay, so first of all, what we do is we take this expression in here and we call it theta. Okay, so in other words, theta equals the inverse sine of 11 over 12. Okay, now before we draw our reference triangle, we have to figure out which quadrant is theta in. So if theta is the inverse sine of 11 over 12, then what that means is that sine of theta equals 11 over 12. Okay. Theta equals the inverse sine of 11 over 12, that means sine of theta is 11 over 12. So since sine of theta is positive, okay, so we'll come up here and we'll say since sine of theta is positive, sine of theta is positive, so theta is in quadrant 1 or quadrant 2. Okay. So remember, the sine function is positive in quadrant 1 and quadrant 2, but which quadrant is it? Well, remember, theta is the inverse sine of 11 over 12. What's the range of the inverse sine function? The range of the inverse sine function was, let's write that in a different color. Range of inverse sine function is negative pi over 2 to positive pi over 2. Okay, and if we were to graph that, well, which quadrant would that put us in? So range of inverse sine function is negative pi over 2 to positive pi over 2. So from negative pi over 2 to positive pi over 2, that's this quadrant 4 and quadrant 1. Okay, okay, so theta equals the inverse sine of 11 over 12. So right away we can just say, okay, since theta is the inverse sine of something, and inverse sine has range negative pi over 2 to positive pi over 2, then theta has to be in quadrant 4 or quadrant 1. Okay, because here's a 0, here's negative pi over 2 down here, here's positive pi over 2 up here. So everything in between is quadrant 4 and quadrant 1. Okay? So since theta is the inverse sine of something, then theta better be in quadrant 4 or quadrant 1. Well, theta has to be in quadrant 4 or quadrant 1. And then from here we saw, okay, sine of theta, well, this means sine of theta is 11 over 12, which means sine of theta is positive. And since sine of theta is positive, then theta has to be in quadrant 1 or in quadrant 2. Okay? Well, theta cannot be in quadrant 2 because theta is the inverse sine of something. And remember, since theta is the inverse sine of something, the inverse sine function has range negative pi over 2 to positive pi over 2. Theta cannot be over here in quadrant 2. Okay? Because if theta were in quadrant 2, then theta would be between pi over 2 and pi. But theta is not allowed to be between pi over 2 and pi because theta has to be somewhere in this interval here. Because, again, theta is the inverse sine of something, and the range of the inverse sine function is this interval. Therefore, theta must be in this interval, which means theta cannot be in quadrant 2. So, in other words, what we just found out is that theta must be in quadrant 4 or quadrant 1, and theta must be in quadrant 1 or quadrant 2, but it cannot be in quadrant 2, we just found out. So theta has to be in quadrant 1. Okay. So just a quick recap of how we determined that. We said, okay, since theta is the inverse sine of something, the range of inverse sine puts us in quadrant 4 or quadrant 1. Since sine of theta is 11/12, that means sine of theta is positive, which means theta must be in quadrant 1 or quadrant 2. So if you're in quadrant 4 or quadrant 1, and you're also in quadrant 1 or quadrant 2, then you have to be in quadrant 1. Okay. Okay, so in a short way of thinking about that, it's always going to work out like that, that if you take the inverse sine of something positive, that's going to put you in quadrant 1. If you take the inverse sine of something positive, like 11/12, that's going to put you in quadrant 1, always. Likewise, if you take the inverse sine of something negative, that's going to put you in quadrant 4. But that's not what we're doing here, okay? Okay, so anyway, using all that stuff, some of which I erased, so theta is in quadrant 1 is what we just found out. Why do we have to know that? Well, we have to know where to draw the reference triangle, because remember, to do this problem, we have to use reference triangles. So we had to know which quadrant is theta in before we can draw our reference triangle. Now that we know where it is, let's draw our reference triangle. So since theta is in quadrant 1, we're going to put our reference triangle in quadrant 1. And remember, we talked about reference triangles a long time ago in a much earlier video. So here's theta. Okay, now since sine of theta is 11/12, remember sine of theta is 11/12, and that's opposite over hypotenuse. So here's theta, so I'm going to call the opposite side 11. I'm going to call the hypotenuse 12. Do we have to label it like that? No, not necessarily. We can. There are a few other ways we can label it that hold true to this sine of theta equals 11/12. But this, I think, might be the simplest way because it'll help us avoid fractions for as long as we can. So anyway, we have that going on. So now what we're going to do is call this side x. Okay, we're going to call that side x. So then from the Pythagorean theorem, x squared plus 11 squared equals 12 squared. Okay. Why are we doing this? Why are we finding x? Well, because we want the cosine of theta, right? Inverse sine of 11/12, we just called that theta, so what we want is the cosine of theta. What's the cosine of theta? Cosine of theta is adjacent over hypotenuse. Okay, this theta is the same thing as this theta. Okay, this theta, that theta, that theta, that theta, that theta, that theta, they're all the same theta. Okay, they're all exactly the same theta. So cosine of theta is adjacent over hypotenuse, so we have to figure out what's the adjacent side. So that's what we're going to do now. So this is x squared plus 121 equals 144. Okay. And then subtract 121 from both sides, so then we have 144 minus 121, which is going to give us 23. So then take the square root of both sides, and then that gives us x equals square root of 23. Now I do want to point out that actually when we take the square root of both sides like that, we actually get x equals plus or minus the square root of 23. But since we're in quadrant 1, x has to be positive, so we toss out the negative solution. So remember, we're in quadrant 1, so here's the origin right here. Since we go to the right in the positive direction, then x has to be positive, greater than 0. That's why we take the positive root only. If we were in quadrant 2 instead, we take the negative root. Okay, but we're not in quadrant 2, we're in quadrant 1 where everything is positive. So x is positive, square root of 23. So we're really pretty much there. That's all there is to it. So cosine, putting it all together now, cosine of the inverse sine of 11/12 equals cosine of theta, right? And why is that? Because the reason is because we took this inverse sine of 11/12 and we called it theta. Okay, we just said, okay, take inverse sine of 11/12, let me call it theta so that I can work with it, manipulate it, figure stuff out about it. Okay, so we took that and we called it theta. So that's why this is cosine of theta. And then what is cosine of theta? Well, let's just go back to the triangle and figure it out. Cosine of theta is adjacent over hypotenuse, square root of 23 divided by 12. And that's it. Square root of 23 divided by 12. And that is our answer. Okay, so cosine of the inverse sine of 11/12 is the square root of 23 divided by 12. Okay, so that's it for example 8 with evaluating trig with inverse trig. And again, we use this flowchart here, and we found out that we had to use reference triangles, and that's exactly what we did. So that's example 8. More examples coming up in the next few videos.